All right, welcome to Lecture 4. We are going to be covering Chapter 1, Sections 4 and 5. We're going to be talking about sig figs and significant figure math. So, imagine you have yourself a brand new pencil. Let's go ahead. There we go. All right, so if you have a regular old ruler, say that it's only marked out in centimeters. And let's, for the moment, go ahead and ignore the actual markings I've made. If you were to measure a ruler on or measure a pencil, a brand new pencil, on a ruler that only measures in centimeters, then the length you're going to get is 19.1 centimeters. Okay. It measures in centimeters. You make the estimate in between the final two markings. But if it measures in millimeters, that is to say, it also has markings in between, so I don't know if you can see them. Doing lots of smaller markings here. All right. Then you're going to get 19.05 centimeters. Okay. Your second measurement is more precise. It has more significant figures. Specifically, this one has 3 sig figs, and this one has 4. Significant figures are a way of talking about the amount of information your measurement contains. Very few numbers are perfectly precise. They're not exact, okay? If you were counting things, for example, I have 2 cats. And this is a precise number. It's perfectly precise. It's exact because it's easy to count individual things. But, any sort of measurement, like this up here, measuring the pencil, there you're going to have significant figures. You need to know which of your numbers are important, which of your numbers matter. How much information does your measurement actually contain? And you have to do that because the measurement isn't perfect. It can't be. Okay. For example, how long is the coastline of England, right? You measure it with a yardstick, then you're going to go over little bits. You're going to undercount other things. If you go over it with, a rule that's only 30 centimeters long, you're going to get a longer coastline just because you're going to be able to measure it more carefully, more accurately. It's just not possible to measure anything precisely unless you're just counting individual items. So, what is a sig fig? Okay. Well, how do we count sig figs is what I should be saying here. First off, any non-zero number in a measurement is significant. Okay. So 134.3 meters. Okay. Non-zero, 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 non-zero. You have 4 sig figs, 4 significant figures. 130 meters, non-zero, non-zero. You have 2 sig figs. So, all non-zero numbers are, all non-zero numbers are significant. So that is the easy bit. The question is, what about the zero numbers? Which zeros are significant? So next up, let's compare 130 feet versus 103 feet. Notice that all my measurements have units. Measurements always have units. All right, so 130 feet has 2 non-zero numbers, as does 103 feet. Okay. But 130 only has 2 sig figs, 103 has 3. Any zero between sig figs is significant. That means that it's part of the measurement. Okay. The reason we have to be careful about our zeros is because the other case where zeros are significant is, and this one is kind of complicated, trailing zeros after the decimal. So a trailing zero means at the right end. So on the left, I mean, you shouldn't have zeros on the left, right? Well, you can if it's a small decimal. You can have zeros on the left, but they have to be on the right to be considered a trailing zero, and it's only significant if it comes after the decimal place. So 100, non-zero number. These two, they are trailing, but they come before. They come before the invisible decimal. So they are not significant. That's why it only has one sig fig. On the other hand, 100.0 has 4 sig figs. Because this right here is significant. It's a 1, non-zero. So it's significant. This right here is a trailing zero, and it comes after the decimal place, so it is also significant. These two are between sig figs. You got a sig fig here, a sig fig over there, so these two are both also significant. So the 100.0 is significant. All 4 of them, I should say. It has 4 sig figs. Conversely, 1010 has a significant 1, another significant 1. This 0 comes in between 2 sig figs, so it is significant. This guy is not significant. It's a trailing 0, comes before the decimal place, not significant. So 1010 only has 3 sig figs. Next up, we have leading zeros. They are never significant. So 0.0001. Well, this 0 over here on the left comes before the decimal place. It's not significant. Okay. These 3, they're after the decimal place, but they are leading zeros. Okay, they're to the left of the number. They're on the left-hand side of the number. So they are not significant. Okay, the only significant number is this guy, the 1. So it's a sig fig. So you have only one significant figure. Conversely, 0.0001010. These 4, these leading zeros, not significant. 1 and 1. Those are each significant. This 0 over here in the middle, that's also known as a captive 0, because it's, captured in between other significant figures. Therefore, it is significant. And finally, we have a trailing 0 after the decimal place, so it's significant. And this number has 4 sig figs. Now, we come to an oddity. What if you want to indicate that a trailing 0 is significant if it comes before the decimal place? So, say you have 100. You need to indicate that this 0 right here is significant. What you do is you add a decimal point. No longer invisible. Okay. When you can see the decimal point right there, that means that you're saying this is a significant 0. So all of a sudden, this number here has 3 sig figs. That is not the best convention in the world because it's really, really easy to miss a tiny little dot at the end of a number. but people still use it. You need to remember it. There is another way, a better way, which we'll get to eventually, but for now, just ponder this. What if you wanted to say that this 0 in the middle of 100 is, but this trailing 0 at the end is not? You can't put the decimal place there, which is one reason I hate it, because then you would have, let's put a frowny face, because no, you can't just put the decimal place there, because then the trailing 0 would be significant and you would have 3 sig figs. You want to find a way to say it has 2 sig figs. We'll get there in just a little bit, specifically when we talk about scientific notation in the next lecture. But let's go ahead and leave that to one side for just a moment and instead talk about significant math. That is to say, doing math with significant figures. Because when you add measurements together, you subtract measurements, you multiply or divide measurements, you need to know how many significant figures your answer is going to have. There are 2 sets of rules, one for addition and subtraction, the other one for multiplication and division. The rule for multiplication and division is a lot simpler. Answer has the fewer number of sig figs. Okay. So if you multiply a number with 2 sig figs times a number with 2,000 sig figs, your answer can only have 2 sig figs. Okay. The lack of precision in the one measurement is washing out the ridiculous precision of the other one. Okay. So, for example, let's do it a slightly more reasonable, 1.25 times 12. Now you do your math. Okay. So the answer is 15. This here has 3 sig figs. This here has 2 sig figs. Your answer can only have 2 sig figs. So the actual answer is 15. Okay. Because it has to have the correct number of significant figures. That is the easy one. That's the simple one. You just count the sig figs in both. Whichever one has fewer, that's how many sig figs your answer has. Addition and subtraction is more complicated. Okay. With addition and subtraction, you're not counting significant figures. What you worry about there is the decimal place. Remember, always remember, never forget, we'll be covering this again in more detail in the next lecture, but when you're adding and subtracting, you can only add and subtract numbers if they have the same units. So like 130 grams plus 1.257 kilograms. Okay? You can't just add grams and kilograms, the units have to be the same. So we do a quick conversion and we have 1.257 kilograms plus 0.13 grams. Why did I not include this 0? Because it's not significant. Okay. So if you were to put a 0 down here, then you would be indicating that you have a significant figure there. Okay. Trailing 0 after the decimal place. And you don't want to do that. Okay, so let's go ahead and get rid of that squiggle. And when you add these together, you end up with 1.287. That should be kilograms. And the answer is in kilograms. Now what you do is you start here at the left and you work your way to the right. And as soon as one of your numbers runs out of significant figures, that's where you stop. Stop when a number runs out of sig figs. Okay, so, boom. Because the number on the bottom only goes to 2 decimal places, the number on the top it goes to 3, your answer is going to cut off there as well. So now that you've done that, you round it, your actual answer is 1.29 kilograms. Now notice that you had 4, you had 2, see, so 2 sig figs, 4 sig figs, your answer had 3. There's no guarantee that that's how it's going to end up. Okay, it won't necessarily end up an average. You could end up with, as many sig figs up here. You could end up with as many sig figs as you had on that side. You could end up with more. You could end up with fewer. Okay, sig figs can be kind of weird like that when you're doing addition and subtraction. And why does it work like this? It's because if you have a really precise measurement and a less precise measurement, the lack of precision is going to wipe out the precision of the greater precision. Okay, so imagine, you very carefully measure the length of, you very, very carefully measure the length of your car. It is, say, 12 feet, 10 inches, and, 3:30 seconds. Now, how far is it to the school? Say that's 5 miles. You add 5 miles to 12 feet, 10 inches, 3:30 seconds of an inch. The answer is going to be 5 miles. The fact that you weren't careful about measuring the distance to the school is going to eliminate the care you took in measuring the length of your car. Okay. So that's what sig figs do for us. Okay. They tell us how precise our answers are. Let's go ahead and work through a few more examples. Let's see. If you go 537 kilometers in 49 minutes, what is your speed in kilometers per hour? Well, this unit is exactly what it needs to be, kilometers, but this one over here is not. You're going to need to convert minutes to hours. So 49 minutes times 1 hour is equal to 60 minutes. For sig fig math, something like this has infinite sig figs. Okay, conversions like that, they are exact numbers. Okay, there are exactly 60 minutes in 1 hour, just by definition. So it has an infinite number of sig figs. So when you're doing a conversion, you're always going to keep exactly the same number of sig figs that you started with. And so when you do this math, you get 0.82 hours. And then you can do, 537 kilometers divided by 0.82. Boom, boom. Okay. And you do a little bit of math. You get 650. Ooh, I should be careful. The answer is 650 kilometers per hour. Note that you start off with 3 sig figs divided by 2 sig figs. Your answer is going to have 2 sig figs. Thus, 650 kilometers per hour. In terms of miles per hour, I'm not entirely sure. I think that would be about 400 miles per hour. So, faster than the speed of sound. Not something you can do in a Volkswagen. And let's go ahead and do another math example. or sorry, addition and subtraction example. Let's see, 10.82 meters minus 1.759 meters. Okay. Now, let's just go ahead and, just so we remember, that's where our last sig fig is going to be. Okay, that's our cutoff. So let's see, 1, 6, 0, 9. Okay, and the answer is in meters. So this is our answer, 9.06 meters. And C, we went from 4 sig figs and 5 sig figs down to 3 sig figs. Okay, addition and subtraction, like I said, it's kind of weird in that way. Okay, it's, you can just lose a little precision, you can gain precision. It seems odd, but that's just the way it works. Or it's not really that you're gaining or losing precision. That's not a good way of putting it. You're gaining and losing information. Okay, I am not well versed in information theory, though, so don't quote me on that. Now, I've mentioned precision and so on a few times, so let's go ahead and talk about accuracy versus precision. Accuracy and precision talk about different ways of improving your measurements, different ways your answers could be wrong. Okay. Accuracy is talking about bias. Precision is talking about noise. Okay. So bias means the answer is always wrong in one direction. Okay, so another way you could talk about that, maybe skew. Okay, your results are always off in the same direction. Okay, so the dartboard is the go-to analogy here. You're aiming for the center, but your answers are all off to one side. Okay, instead of hitting the bullseye, you're over here. Okay, so there's your bias. Precision is talking about noise. Noise is just randomness. It's easy to see or hear noise when you're looking at digital measurements because they faithfully record everything. So you always get to see, the needle is bouncing around. You get these the random fluctuations, right? Or when you listen to any sort of recording or just a silent room, you'll hear the white noise in the background. Or you turn on a TV, once upon a time you'd see static. That was just random noise. So let's go ahead and draw two things. This one is precise, this one is imprecise. So this one is precise. Your answers are all, tightly grouped. For the imprecise one, you have a lot of noise, a lot of random error. That means you're off in all directions rather than one direction. And so you have a widely scattered set of data points. Okay. So that's the difference between accuracy and precision. Accuracy is talking about bias or skew, and you fix that. Fix it with calibration. Okay, calibration is when you record a result you already know the answer to. Okay, you measure a weight that you already know, or you hit the tare button on the balance, things like that. So that will remove any systematic bias, okay, in your measurement. For precision, to get rid of noise, you have to. You just have to eliminate noise. Eliminate sources of random error. Okay, so for your balance, one way you can do that is you have your balance. Here's your pan, and you put the entire thing inside of a glass case. Okay. That means that no air, no breezes are getting in. There's nothing. Okay, it makes the environment much more stable. And they do that. They actually do put violences in glass cases. When you're trying to measure, micrograms or nanograms, then you need a very sensitive balance, and you want to not have to sit there and watch, random puffs of air, just make it impossible to measure anything. So you seal off the environment, and you control it as carefully as you can to eliminate noise. To eliminate bias, you just have to calibrate. It's a little bit more direct. Yeah, everybody worries about noise. Bias calibration is fairly straightforward. All right, and that does it for this particular lecture. Next time, we'll be talking about units and scientific notation and all sorts of fun stuff like that.